Hello, my name is Sviatoslav Mychka. I am a co-author of the paper Binary Data Compression using combinations of entropy and dictionary encoding algorithms. Today, big data is stored in various distributed databases and file systems. They allow storing different files on different servers with the ability of restoration using duplicates. Big data is the term that does not mean a specific amount of data, but rather its relationality to other data. The big data is usually stored in such database formats as Parquet, which is supported by Apache Hadoop distributed platform, and supports different compression algorithms such as LZ4 or Snappy. Binary data compression plays a crucial role in distributed systems by reducing storage costs and improving processing efficiency. Unlike specific compression algorithms, the algorithms designed to work with binary data treat any information as a sequence of bits and bytes. This means any data may be encoded and then decoded without errors or losses. Two most popular entropy encoders, which are Huffman optimal encoding and arithmetic encoding, are widely used in methods like deflate, pzip2, and others. Usually, they are used in combination with dictionary encoders, which include LZ4 and Snappy, mentioned above, and also other algorithms with similar idea. Even though LZ4 and Snappy are designed to avoid entropy coding, the main goal of the paper is to investigate how would these algorithms work if combined with different types of data. The implemented method should be tested, and the results of experiments should define the practical value of such encoding. Entropy is the main concept in data compression. As it comes from Shannon's source coding theorem, entropy defines a threshold after which lossless compression is impossible. Dictionary coding is used to detect and utilize patterns, while entropy coding tends to increase the entropy of the message. As mentioned before, LZ4 and Snappy use only dictionary encoding, but other algorithms like deflate use combinations of dictionary and entropy encoding, trading time for the overall compression ratio. Huffman coding is a data compression method designed to ensure optimal encoding for each separate symbol. It was designed by David Huffman in 1952 and originates from the Shannon-Fenot coding. Arithmetic coding encodes the whole message into an interval from 0 to 1. However, in practice, arithmetic coding is usually designed to work with integer numbers. It was originally described by Jorna Rizanin in 1976. In the experiments for this paper, we used the adaptive version where the probabilities of each symbol are set to 1 and then updated. LZ4 and Snappy are both designed after LZ77 and belong to the LZ family. Snappy is usually faster than LZ4, but gives much lower compression ratios. LZ4 has different levels of compression, but Snappy didn't outperform the first level of LZ4 on the test data, mentioning the compression ratio. The implementations of these algorithms were taken as black boxes without modifying the original behavior. To test the algorithms separately and in combinations, we used a part of Silesia corpus, a set of different files used in everyday computer work for testing compression algorithms. The files selected for the testing are in the table below. Here we have the file named Dickens, which contains English text, just plain English text, Mozilla, that contains executables of the popular web browser Mozilla, its Unix edition. MR is a magnetic resonance image. NCI, a database of chemical structures. SAO, plain binary data of the SAO star catalog. And XAML, which consists of formatted XAML files. The Huffman and arithmetic coding algorithms were implemented using C#12 and .NET 8. The LZ and Snappy algorithms implementations were taken from official GitHub repositories. In most cases, arithmetic coding resulted in higher compression ratios than Huffman coding, but the difference was rarely significant. Usually, LZ4 worked slower than Snappy, but the compression ratios Snappy gave exceeded only the first level of LZ4 in simple text files. Using entropy coding after Snappy in most cases raised the ratios more than it used after LZ4 of any level. XAML file was a good target for LZ4 and Snappy, but Huffman and arithmetic coding gave compression ratios almost as low as for the executable and plain text files. The entropy encoding algorithms were slightly better with an image and a database. It's also worth noting that the entropy algorithms, if used after Snappy, they still couldn't outperform the same algorithms used after LZ4 in any tests. And as the conclusions, the dictionary encoders widely used in distributed platforms can give satisfactory compression ratios with structured data, performing operations at high speed. The results obtained show that using relatively slow Huffman or arithmetic coding after fast dictionary encoders can increase compression ratios, but require more time for compression and decompression. Combining dictionary and entropy encoders allows to mitigate the impact of high entropy of binary files. The topic is valuable for further development of various distributed platforms, databases, and other information storage structures. There are significant results shown that the algorithms combinations are good for compressing structured databases, but also they can be useful in advancing compression ratios in the conditions of limited storage size or internet traffic. The combinations of entropy and dictionary compression may be expedient for the systems that do not require frequent or fast access to the data. For example, it could be some archives or big databases that are not accessed very frequently, but still contain the big data or internet web pages that consist mostly of the XAML file format mentioned above. And for such systems, the combination of LZ4 and arithmetic coding is the most suitable, mentioning that LZ4 is the most performant if used with the fourth level of compression. It is worth noting that using LZ4 with the compression levels higher than the fourth did not bring higher compression ratios, but increased the time significantly. The topic is valuable for further development of the distributed platforms, and also in the future we plan to develop and compare other compression algorithms, including the ones that use machine learning ppm or context mixing for predicting the symbols' probabilities. Thank you for your attention.